You wake up and glance at your phone. The screen gives you an exact time even though the curtains are closed and you have not seen the sky. Outside, cars, schools, offices, and signs repeat nearly the same numbers. You do not need to watch the sun, identify a star, or measure a shadow. Then every display goes dark. The numbers vanish. How would you know what time it is now? The city fades into open ground beneath a bright sky. A simple upright post casts a long morning shadow. As the sun climbs, that shadow shortens, reaches its smallest point, then stretches in the opposite direction. For most of human history, time was not waiting as a number on a screen. It had to be read from changes in the world. But noticing change was not the same as measuring time in fixed units. Before people divided days into hours, they learned that the world returned to familiar patterns. Light became darkness, and darkness became light. The moon grew, rounded, faded, and disappeared before beginning again. Rain arrived and withdrew. Plants flowered. Animals migrated, gathered, or gave birth at recognizable times. These changes could guide travel, hunting, gathering, planting, and ritual without providing an exact hour. Early timekeeping often meant knowing when something important was likely to return. There was a difference between sensing change, recognizing a cycle, counting repeated cycles, and measuring a fixed interval. Each step required memory, comparison, and eventually a shared sign that others could understand. The earliest observations left almost nothing behind. A person could remember lunar phases or anticipate a wet season for a lifetime without producing an artifact. A marked bone seems more promising because it survives. Rows of notches can look like a count, and some researchers have proposed that certain prehistoric bones recorded lunar cycles. The problem is that a mark does not explain itself. The same pattern might represent objects, events, arithmetic, ownership, or something we have not imagined. Calling every repeated notch a calendar would turn an interpretation into a fact. The same caution applies to monuments. A wall aligned with a sunrise is not automatically a complete calendar, and a tall object that casts a shadow is not automatically a sundial. Archaeology compares orientation, context, repetition, associated objects, and the explanations that still fit the evidence. Uncertainty does not weaken the story. It suggests that timekeeping was probably older, messier, and more gradual than any single artifact can reveal. One way to make a recurring event easier to recognize was to anchor it to the horizon. At Nabta Playa, in what is now the southern Egyptian desert, late Neolithic communities arranged stones in ways associated with cardinal and solstitial directions. Such an alignment could help mark a turning point in the solar year, when the sun reached an extreme position along the horizon. That did not necessarily make the structure a complete calendar. A seasonal marker could still be valuable without counting every day. In an environment where rainfall, water, migration, and gathering cycles affected survival, recognizing an approaching seasonal change could guide an entire community. The monument may also have served ritual or social purposes. Ancient structures rarely needed only one meaning. Still, a single marker had a limitation. It could announce an important point without showing how far the year had progressed. At Taosi in northern China, observers may have used a more organized way to watch the sun. Archaeologists uncovered the foundation of a curved structure with a fixed observation point and a series of openings or slots. From that position, the rising sun would appear through different parts of the structure as its location on the horizon shifted through the year. Some alignments fit important seasonal dates, including positions near the solstices. The system appears to have supported repeated observations rather than one annual event. It did not display a numbered date like a modern calendar, and every opening may not have had one certain purpose. It did show how architecture could make the moving horizon easier to compare. Knowledge no longer depended only on one person's memory. A built reference could preserve an observation for others, although it still required clear skies and a fixed viewpoint. At Chankillo, on the coast of Peru, builders turned an entire ridge into something like an artificial horizon. 13 towers stand in a line. From designated observation points, the rising or setting sun appears at different positions along that sequence as the year advances. Near one seasonal extreme, it appears toward one end. Months later, it shifts toward the other. Positions between the towers provide additional references. Chankillo was more informative than an alignment marking only one solstice. Observers could estimate where they were within a much larger part of the solar year. It did not tell them the hour of the day. It answered a different question: how far had the annual cycle moved? A timekeeping instrument did not have to fit inside a room or rest in someone's hand. A landscape could become a measuring system when people shared a viewpoint and interpretation. Annual markers answered one kind of question. Daily life created another: how far had the day already passed? A stick driven into the ground offered a simple clue. Its shadow stretched long after sunrise, shortened as the sun climbed, reached its minimum near midday, and lengthened in the opposite direction during the afternoon. In ancient Egypt, surviving shadow clocks show how this basic observation became a deliberately designed instrument. A marked bar received the shadow of a raised crosspiece, and the device could be turned around after midday. It did not create modern clock time, but it divided daylight into recognizable parts. A shadow could organize work, ritual, travel, or observation more precisely than a general sense of morning and afternoon. Yet it inherited every weakness of sunlight. Clouds erased the reading, night stopped it, and seasonal daylight changed the length of every part. Imagine dividing every period of daylight into 12 equal sections. In summer, sunrise comes early and sunset comes late, so each section lasts longer. In winter, the same 12 sections must fit inside a shorter day, so every section becomes shorter. Ancient seasonal hours worked in this general way. They were equal divisions of the available daylight or darkness, not fixed blocks of 60 minutes that remained identical throughout the year. The system made sense when daily routines followed the sun. It also meant that an hour changed length across the year, and that daytime hours could differ from nighttime hours on the same date. The idea seems strange because modern clocks hide seasonal differences behind equal units. Early timekeepers were answering another need with another definition. A shadow showed which part of daylight had been reached. At sunset, a different signal was needed. The night sky offered another moving pattern. In ancient Egypt, observers tracked selected stars and groups of stars that appeared at different times through the night and during different seasons. Instruments called merkhets helped trained observers establish a north-south line and watch for a chosen star crossing that meridian. The instrument did not display a number. It created a stable reference against which celestial movement could be compared. When a particular star reached that line, an observer could identify a portion of the night. This required knowledge, practice, and a clear view. Clouds interrupted the system, visible stars changed through the year, and local surroundings could block observations. Even so, star time extended timekeeping beyond sunset. The remaining problem was dependence on the heavens. Measuring an interval indoors or under clouds required something that kept changing on Earth. Water provided that change. In an outflow clock, water drained through a small opening while markings inside the vessel showed how far the level had fallen. In an inflow design, water entered another container and raised a visible level or float. Either method could measure a duration when the sun and stars were unavailable. Egyptian clepsydras were used at night and in ritual settings where repeated intervals were more useful than a shadow's position. The idea was powerful because it turned a physical process into time. Yet water was not perfectly obedient. As its level changed, pressure could alter the flow. The shape of the vessel mattered. Temperature affected the liquid, and cold conditions could stop it completely. Makers adjusted shapes, openings, and scales to reduce these errors. A water clock was valuable not because it was perfect, but because it made intervals repeatable and independent of clear skies. In Han China, surviving artifacts show sundials and clepsydras operating as parts of a wider system. A sundial used the sun to establish a reference, while a water clock continued marking intervals when a shadow was unavailable. Because water flow could drift, the solar reading could help check or correct the clock. Progress did not always mean replacing an imperfect device with a perfect invention. Different methods could expose one another's errors. Other regions developed their own water-based solutions. In South Asia, a small bowl with a hole could float on water, fill gradually, and sink after a repeated interval. The design differed, but the principle was familiar: turn a controlled physical change into a shared unit. These examples do not prove that every society followed one line of invention. They show different communities solving related problems with local materials, knowledge, environments, and needs. Once intervals could be repeated, timekeeping began to organize people as well as describe nature. A water clock could limit how long someone spoke. A burning candle or incense trail could mark a ritual period, a work interval, or a watch through the night. In parts of East Asia, incense timekeepers turned the steady progress of burning material into an audible, visible, or scented signal. The important change was social rather than purely mechanical. A measured interval mattered because several people agreed to act when it ended. Someone stopped speaking. A guard changed position. Water was allocated. A ceremony began. Time moved from private observation toward public coordination. No device had to be perfectly accurate to transform behavior. It only needed to be consistent enough for its purpose and trusted by the group using it. Timekeeping was no longer simply reading nature, it was becoming a social rule. Now return to the phone in your hand. Its numbers look completely different from a stone alignment, a moving shadow, a star crossing a meridian, or water falling inside a vessel. Yet all of those methods belong to the same long transformation. Nature supplied recurring change. Human memory recognized patterns. Marks preserved counts. Architecture fixed observations in shared places. Instruments divided days and measured repeatable durations. Communities turned those measurements into expectations that other people could follow. Humans did not discover hours already hidden in the world, waiting to be read. They created increasingly reliable ways to agree on where they were within a cycle and how long they should wait before acting again. The clock on a screen is the latest layer of an ancient agreement. Time becomes useful when people can measure it, share the result, and act together.